or Coecke, mathematician, physicist, computer scientist, musician, many other things. So Bob's career took him through many academic and non-academic institutions, including DUB, Imperial Experimental Institute, Cambridge, Oxford.
Cambridge here, mathematics.
Exactly, great. So we are very happy to have him here today, representing University of Oxford and Quantinuum. And Bob will talk about AI interpretability with quantum perspective.
Okay, thanks so much. It's good to be. Like I say, I was a postdoc here a long time ago in the maths department. So at the moment I'm working mainly for Quantinuum, which is a quantum computing company, which now kind of recognizes the largest integrated quantum computing company. We're here in Cambridge. Ross Duncan, who's sitting there, he has a team here in Cambridge. I've got a team in Oxford, and this is our logo. You see this thing in the middle. So you see a C for compositional, you see an I for intelligence, you see a Q for quantum, and then unfortunately it turned out to be a skull in the end. But yeah, that's something we have to learn to live with. I'm going to give a little prologue before. Let's see if I find the arrows here. Okay, that's the other. So let's get quantum right first before we're going to do quantum AI. So that's John von Neumann. And John von Neumann, of course, is the father of the quantum mechanical formalism. But at the same time, he published his book in 1932, and then in 1935 he said, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So 3 years after publishing his book with the Hilbert space formalism, he pretty much denounced this himself. And then he came up with a whole bunch of new stuff. None of it really made it in quantum textbooks, but each of them was pretty much a new area of mathematics in some way or another. So it was a useful thing to do. So this is Erwin Schrödinger. Something Erwin Schrödinger said in 1935, the same year, going against the spirit of what von Neumann was proposing. Von Neumann had been proposing the projection postulate and put all the focus in quantum mechanics on quantum measurement. But Schrödinger said in 1935, the most important ingredient in quantum mechanics is not measurement, but entanglement. What happens if you put two systems together? Composition. And many people try to come up with new formalisms, following sort of von Neumann's request. We need to come up with something different than Hilbert space. Most didn't make it anywhere in textbooks and stuff like that. So going back a long time, 2003, 2004, we started to try to build a new quantum mechanical formalism, mainly following Schrödinger's idea that composition of systems should be like your prime actor, your number one actor of your formalism. And so anyway, that's what I'm saying. That's what changed. When two systems enter into temporary interaction, I would not call that one, but rather the characteristic trait of quantum mechanics. But nobody really picked this up. This only became sort of, this statement of Schrödinger, only people started to give attention to it after teleportation and all these important things came out of entanglement. So in 2016, 2017, Alex Tischinder and I, we published this book, which was at a time like the quantum computing course at Oxford. And it was basically an entirely diagrammatic formalism, which we taught, following the idea that composition is your number one citizen in your quantum mechanical formalism. So I'll tell a little bit about that, but also my story about AI is going to use the same formalism. It's going to use exactly the same formalism. So that's why I'm giving this little prologue. So we're still, I mean, we start teaching this 2013, 2014 in Oxford. So it basically teaches all your fundamental quantum concepts, your algorithms, everything using this picture. And then we also derive Hilbert space from the diagrams. We derive Hilbert space from the diagrams. Now, so I mean, this is like a 1,000-page book, and then you write another book. Why would you write another book? So this quantum in pictures with pretty much the same content, but there's no Hilbert spaces anymore here. So this is something I wrote with both Alex Tischinder and Stefano are former PhD students of me in Oxford. They're both faculty there, so they pretty much took over my group, like Alex Kissinger and Stefano Goglioso here. They pretty much took over the group I had been building there together with Samson Abramsky. Now what's special about this book is what's on the back. Hello there, want to learn about quantum? Maybe you think you don't know enough maths. Well, that's not a problem. The pictures in this book are a new kind of maths that will teach you all about the quantum world, and which have a very low entrance fee. Very low. So technically, when you're in UK, 7-year-old, you're learning everything at school that you need to learn this book. 7. That's the necessary age to start this thing. Okay. We did a bit of an experiment, and so this is an article from The Guardian from last Christmas, something like that. It's easier to convince kids than adults about quantum mechanics. So this is the result of an experiment we did last summer, and I'll explain a little bit what we did. So we took the entire book and we turned into lectures. Like you see, this video lectures is taken in my blackboard in my office. We took some exercises around it, also videoed exercises which we created around this book. Essentially what we were doing, we were setting up a course, we were mimicking a course, a typical postgraduate course at Oxford University. So a typical postgraduate course at Oxford University is like 8 weeks of lectures. You get 2 hours of lectures each week or something like that. Then you get an exercise sheet, you try to solve the exercises, then you get an hour with a tutor. The tutor explains what he did right and what he did wrong, things like that. So we were completely simulating that format of an Oxford University postgraduate course. We did a call in the UK, that's for legal reasons and stuff like that. We did a call in the UK and we said, who wants to get a free course in the summer? And everybody who takes the course gets a certificate. We got thousands of candidates from UK students. We randomly selected about 60. We gave them a course over the summer. Wasn't ideal because some go on holiday, some do this, some do that. But anyway, we were running over the summer over a period of 2 months to mimic the 8 weeks of Oxford University. And despite the fact that we said everybody who takes the course gets a certificate, we said, okay, we are going to ask you to do an exam, nonetheless, and do your best, please. It's for us. It's not for you, it's for us. And we kind of secretly said, if you do really good, then you can have it on your certificate, your marks, so that at least you would get some advantage from doing the exam. So essentially the exam, so we had the ages of the kids was like 15 to 17, 18 years, high school kids, like I said, pretty randomly selected from different kind of schools. And we gave them, actually in the end, an Oxford University postgraduate exam. They didn't know that. We just took exercises from Oxford University quantum courses. And 50% of the kids got distinction. So yeah. So I mean, there is something to that new formalism, you know, like kids can do it. And so here is some of the statistics we got, like left top you see prior knowledge of quantum, there was mainly nobody. How much time did they spend? Hours per week. The majority 1 to 2 hours a week on the course. So it was not that they were full-time, like working hard on it. The bottom you see that actually state school, grammar school, private boarding school, they're all around 60%. There was no much difference in the results. Pretty much the same. And then maybe the nicest table is the one top right. Impact on the course of the participants. The course strengthened my motivation and confidence. Strongly agree, the majority. The course motivated me to pursue a STEM career. Again, majority agrees. So that was the impact of this. Since the article, oh, didn't I put it? Okay, tomorrow I'm going to say a bit more about this stuff. Tomorrow I'm going to give a 2-hour course, 9:30 to 11:30, I think, and I'm going to go in much more detail about its forms. I just want to give you a little taste how it works. So the things we're working with are spiders. We call them spiders. So that's a formalism. Ross Duncan there, again the same guy, and I came up with somewhere in 2007, 2008, which is called ZX calculus. It's made up of spiders. And the rules are very simple. Like if you connect two spiders, these are like tensor networks. You connect them with 2 spiders, they just fuse together. If they're of the same color. If they're of a different color and they share 2 legs, then the legs vanish. That's 2 simple rules. Same color, they fuse, different colors, the legs in the middle vanish. This is quantum circuit. We're going to simplify this. So the way to see this as a quantum circuit is, okay, you got 3 qubits, these 3 lines, and then you got 3 Zenon gates, which are acting on this qubit, like first two. And then you forget about all of that, and you say, okay, what are we going to do now? What we're going to do now is like, okay, we see things of the same color, so we just fuse them. We see 2 wires between red and green, we get rid of them. That's basically how you do this thing. Now, this is a very simple example, but this is part of the state of the art, how you simplify a quantum circuit now. This is really part of the state of the art. Which you stick this in compilers, you stick this on all your technology, and in general, lots and lots of stuff which people are now using in quantum computing. You can go to IBM, you can go to Google, of course, you can go to Quantinuum ourselves, you can go to all the photonic quantum companies in particular. They're all using this now. They're all using this as part of their main language. So here, this is some sort of optimization stuff. So this language is also very practically used now, widely in quantum industry, especially quantum industry. So, okay. And very soon we will release all our exercises and stuff like that. It's just taking some logistics to get this, but all our materials will be released soon. Okay, and now let me go to the topic I really wanted to talk about, which is AI interpretability, but we'll build further on the same language yet again. That's why I'm saying this. So we now have a problem, like, I mean, everybody's talking about AI, blah, blah, blah. I mean, when they say AI, they just mean, of course, machine learning, large language models. Well, AI is much broader, but okay. So large language models such as ChatGPT have deep-seated and systematic problems. Nobody knows how they work. Hence, behavior can't be controlled, accounted for, nor predicted. Now, a deeper problem maybe is where to go next. We are somewhere where to go next. If you look at the history of science and technology, then lack of understanding typically results in a dead end. We've seen this with the Babylonians, which at a time were so much better than the Greeks in a lot of stuff, but in the end we only talk about the Greeks anymore, we don't talk about the Babylonians anymore. Ptolemy had a fantastic system, which secretly even had relativity theory built in, but we don't use, actually they use it for Google Maps, I think, still, Ptolemy's system, because if you're on Earth, it's okay, it works. But anyway, typically we are now dealing with something that we don't understand, so how do you go further? How do you do science? It's not really how science has usually been progressing. Now I'm going to specifically talk about quantum machine learning. Quantum machine learning is a field, I don't know how many papers have been written in quantum machine learning, thousands, probably more. Does anybody have a guess how many? Thousands or 10,000 or 100,000? Something like 1,000, many thousands. So quantum machine learning requires training at scale, of course, like any kind of machine learning, but there's no theoretical results at the moment which guarantee that you can actually do that. And a lot of leading people in the field are kind of leaving the field now or pausing to do work in the field because there's no guarantee that you're going to get anywhere. And the machines are not there yet to try. You have another way is just to try on machines, like people do in classical ML. And machines are not there, so you can't just do it, so you have to wait a little bit. And the thing like with sustainability is a serious problem, like I just said, for the field of QML as a whole. And there's a, yeah, people, I'm not going to name names, but I met a few people the last few weeks and they all say, yeah, we're not going to work on that anymore for now because, okay, now I'm going to do something, so introduce some key concepts of the sort of framework I'm going to set up for like quantum-enabled interpretable artificial intelligence. Like, so the principle I'm going to refer to, and this goes back to what I mentioned about Schrödinger, you know, composition of systems, is compositionality. Now, Schrödinger mentioned that composition of quantum systems is like, for him, the most crucial thing about quantum, more even than measurements. And like I said, the language which I show is totally based on like composing systems. Like compositionality is also key to computer science as a whole. Without compositionality, you wouldn't have a mobile phone. It's as simple as that. Because the way people now compose or build software and hardware is basically where you take small pieces and then you make them interact in a certain way that you understand, and then you build big complex systems. That's how computer programmers work. That's how hardware designers work. And it's all this principle of compositionality, which goes back to linguistics historically. It goes back to, well, it's attributed to Frege, but it's probably older, much older than that. But the idea of what people call Frege compositionality is you understand the whole if you understand the parts and how these parts are put together. This is exactly what happens when you say a sentence. You understand the words, you know how the words are put together like grammatically, and then you understand the meaning of a sentence as a whole. That's the idea of compositionality. It comes from linguistics, but is widespread use now in computer science. It's essential to actually do computer science. Now, if you look at this traditional definition of Frege, of compositionality, it doesn't really work for quantum composition. Because if you think about a maximally entangled state, there is really no point to say, okay, we understand the parts and then how they're put together, because your parts are just noise in a maximally entangled state. So the concept doesn't really hold anymore. And the change that happens there is that the sort of bottom-up thing from words to sentence needs to be complemented by a top-down thing too, where the whole also tells you something about the parts. Like for example, the entangled state tells you your parts are noisy. It's a much more natural way to think about it. And the same is true actually for modern NLP. The meanings of words are very much determined by the context. You train in context, you train in bigger text, that's what people do. So it's also a top-down flow of meaning, so quite much more similar to what we see in quantum, sort of the way meanings flow in language. Yeah, I mean, I'm just showing some papers like that. Oh, sorry. That's a paper I wrote about like how we should change our conception of compositionality from quantum. Here we're trying to define like what compositional interpretability means for explainable AI. So I can share, I'm happy to share my slides if you want to go look at them. Here is an example of something that's not compositional in the sense we want it. This is like you see a little bird on the left, you see a bunch of notes in the middle on the right. None of these have anything to do with the parts of the bird. This is a counterexample to what you don't really want. You want, while this right-hand side is composed from plugging things together, it has nothing to do with how you plug the bird together, at no level. And nobody really knows what stuff on the right-hand side is actually doing. So this is an example of how you need to, when you say the word composition, of course people say, yeah, this is compositional, but it's not in the right way. And I mean, here I'm trying to, I mean, this is not something that's out there, but the idea here is that the compositional structure of the mathematical model reflects the compositional structure of the phenomenon. If you get a phenomenon that in some way is plugged together, they want the mathematics that describes that phenomenon to respect that same structure of plugging it together. It's a very natural assumption, but it's not true for neural nets and things like that. It's a very natural assumption. It's something we've always been doing in science, that sort of the structure of the phenomenon reflects the structure, the mathematical model reflects the structure of the phenomenon. And I mean, this is like a definition about how compositional something is. So you see the P is the phenomenon, then you got this I, which is interpretation as a mathematical model, and then you want to see how much the C is compositional structure, how much compositional structure is factors over and is actually respected in both sides. Yeah? So that's what I mean by compositionality. It's not just that you compose something together, it's that there is a representation in what you compose in your mathematical model of what you're actually trying to model, which is a perfectly reasonable assumption, which, I mean, perfectly reasonable. There's nothing more you can say about it. Okay, now I've got another definition. And if you're going to remember anything from this talk, if you're a quantum computing scientist, then it's probably this definition, and then you think about it, and you may think that it's nonsense, but not. So, I said, if for a phenomenon under well-established assumptions, the quantum formalism is a necessary description, then we call it effectively quantum-shaped a theory. This doesn't mean that this thing has to do anything with physics. It just happens to be the case that under some reasonable assumptions, for a certain phenomenon, you end up with quantum formalism. I'm going to give an example, of course. I'm going to give an example of something like that. And it has to be provable. And you'd be surprised how many times this shows up. Okay, and this, I mean, I'm going to be flexible. This assumption may be like foundational, or engineering. If I get with quantum formalism for engineering and foundational reasons, okay, then there are reasons to believe that there may be some that you may try to put it on a quantum computer and see whether you can get some advantage, whether it's physics or not. And so this is opposed to what I would call intrinsically quantum shaped. Now we're talking about chemistry, we're talking about materials, the stuff which really is physical quantum. So these things, people, of course, that's what Feynman first came up with. He said, if you're going to stick something on a quantum computer, then just take quantum stuff itself, like chemistry, like materials. Because if you're going to do this on a classical machine, you're going to get in trouble. I mean, we saw in your talk, you were referring to that. That's what I call intrinsically quantum shaped. But maybe there is stuff which is not like physical matter, but that also drives you in the direction of like quantum formalism. And then you may also hope for the same reasons that there will be some advantage to it. Trying to do it in a quantum computer. Okay, I'm doing well with time. Okay, we describe an example. I'm going to talk now about text circuits. So text circuits are a new ingredient of former linguistics, if you want, which came out of a development I've been involved in since maybe 2007, 2008 too, and I'll try to explain what they are. So you've got the old theories of mathematical linguistics, going back to Jim Lambeck here and Noam Chomsky, you all know. And what these people did, they tried to understand how words compose together to make sentences and how you can actually generate valid sentences and things like that with generative grammars. And so there was a lot of work done, and I call this traditional compositional structure in language. It's typical about like grammar. It's really about, can we give mathematical form to grammar? Can we mathematize what grammar is and how we plug words together and how you make well-formed stuff? That's what they. And in 2008, like when I say linguistic theory there, in 2008, Bernoulli, Steve, and I, we addressed the following question: like, if we know these theories about grammar, going back to Chomsky and Lambeck and stuff like that. Now, at that time, like the idea of representing meanings by vectors, like people now doing large language models and in AI, was starting to come up, although it was still academic. There hadn't been like any deep learning revolution yet, nothing like that. So it was an academic thing, and Steve, who worked with us, happened to sort of study what can you do practically if you represent meaning by a vector, meaning of a word by a vector. Now, something nobody had ever done was basically mimic the compositional structure, like which these linguists had been using to see whether a sentence is grammatical, to actually take the meanings of words and produce the meaning of a sentence from them, using the interaction structure. So really lifting this idea of compositionality from just structure, grammatical structure, to meaning. That you actually compose meanings of words together to build the meaning of a whole. And so we came up with a formalism, and that's in the top paper at the left. But basically, what we used, okay, I'm going to go a lot of slides back. We just use this to do that. We really just use this. Because in this book, basically in 2004 or 2005, when I just started to do this diagrammatic language, I mainly went around the world explaining people what teleportation is with pictures. Teleportation is with pictures. I think I got a picture somewhere. Okay, yeah, here you see teleportation with pictures on the left. And you see that? It's just like this piece of wire that you can then yank. And I went to Montreal, and Jim Lambeck, whose picture I just showed, was in Montreal, and I gave a talk, and I was explaining teleportation, and Jim Lambeck said, "Hey, Bob, this is grammar." I said, "No, Jim, this is physics, quantum physics." He said, "No, this is grammar." Because he realized that the sort of diagrams that I was using is exactly the same as some of the formalisms he came up with to represent grammatical structure in language. It was exactly the same thing. And therefore, so what we found in this book was basically, we have wires. What is supposed to flow in the wires? Vectors, because that's quantum states. How are the wires organized? Like grammatical structure. So I said, okay, maybe we can just use this to combine meaning and grammar. And then we did a lot of experiments. Okay, now I'm going forward again. We did lots and lots of experiments. Oh, where are they? I don't have papers with experiments here, but we lots and lots of experiments, and it worked. It worked perfectly. And I'm not going to explain this in detail because this is not what I want to focus on today. But once you understand and you see it, you say that's perfectly natural, like using this quantum formalism to really model how the meanings interact. It's vectors. It's vectors interacting through structure which are called compact closed categories, which have cups and caps, and they can go up and down. I'm not going to give an example here of that picture because that took me too far. But anyway, so we came up with this theory in 2008 on how to combine meaning and grammar. And then in 2016, with Will Zhang, who was finishing his PhD then with me, we basically realized that if you would then stick this formalism on a quantum computer, you would get quantum advantage for most of your tasks you're interested in natural language processing. So you would get, I mean, typical groover style advantage, no more, just groover type, like a quadratic advantage of some sort. And then, so that's the bottom left, and then I'm now going to go to bottom right. Then in early 2020, we actually were able to do on a quantum computer, an IBM quantum computer, effectively quantum natural language processing. We did it and it worked pretty well, everything worked pretty well, the training worked pretty well, very small scale at the time. And then now, so we have the software package available, and that's top right, left, called Lambeck, after the guy on the left here. And this you can download, it's all open access, it's everywhere and very well documented, and you can yourself now do quantum natural language processing in this style tonight, even if you want to. So that goes now a while back. Huh? But this is what I called like the old traditional compositional structural language. Now I'm going to go to the new one. And these are the stack circuits which I introduced in a paper in 2020, and I'll give you an idea of that words. So it's a little bit different. In a way, it encompasses all this grammatical stuff, but I'm just going to give you a simple idea on how it works. Okay, I've got a little text here. Alex meets Bo, Bo marries Chris, Alex kisses Bo, whatever. So how do you represent this as a circuit? Like this. So you got Alex, Bo, Chris, first they meet, then the other one marry, and a natural thing to do, natural. So Alex meeting Bo is like you entangle them. Bo marry Chris, you entangle them. That's even more entangled. And then well, that's kind of disentangling, but okay. But you see the idea. Turns out you can do this for all of English. For any grammatical construction, you can actually build a circuit like that. So there's an algorithm that takes all of English, or any language for that matter, and takes it into circuits. So this is a paper where we provide the algorithm. Doesn't matter that you understand this, but this is sober Alice who sees drunk Bob clumsily dance laughed at him. So this is Chomsky-style generative grammar formalism. It doesn't matter, we just use that because this gives us an algorithm that turns this exactly in this circuit. You can sort of look at Alice is sober. You see Alice sees Bob dance. See, there's higher order stuff going on. You've got nesting of boxes and stuff. Because if you've got an adverb, it modifies a verb, and so on. So there is higher order stuff going on. Yeah, but it's still a circuit. It's still a circuit. With some higher order elements, and it's easy to make them. Now, one of the magic. So the initial idea was to change, to lift from reasoning from word to sentence to text. And basically, what we are doing here is we're connecting different sentences up through the agents, through the nouns. That's literally what we're doing here, because these are three sentences and I connect them up, which was not something you could do with the old Lambeck-Chomsky formalisms. But that was the initial goal, and then we realized that actually these circuits were language neutral. Like if I do I really love you or je t'aime vraiment, you just get the same circuit. And we realized that for all languages the circuits become the same. So it's something, it's probably what Chomsky really wanted, universal language, which he didn't really entirely get. And also different styles, if you have a lot of short sentences or one long sentence saying the same thing, you always get the same. So it's some sort of language neutral or style neutral representation of how meaning interacts. So in a way it's more fundamental. Anyway, we got these circuits. So yeah, let me just skip this slide because I'm getting old. So basically, we have an algorithm that takes us from text to circuits, and then if you stick in the concrete language and a style, it takes you back to text. But it will be different for every style. But we got normal forms. We got canonical backward algorithms, which gives you a normal form, language in a normal form, so we got all that, but it's still different. Okay, now here, remember, I was talking about compositionality and compositional interpretability, like that. The structure in the phenomenon should be reflected in the structure of the mathematical model. And then machine learning practice is basically you represent your meanings by vectors. You can prove that under these two assumptions, these texts I was talking about, these text circuits, require a quantum mechanical model with vectors and tensor product. Tensor product you prove, you derive that you need it to do this. It's not something you choose, it's something you derive. So you end up with something that I call effectively quantum shape. It's also important people use negatives too in these vectors. It's very important. This gives you a ridiculous dimensional reduction to use negatives. So you end up, and now they're starting to use complex numbers too in practice. Because again, it makes things a lot better. So this is an example where I say, okay, this texting forces you into quantum formalism for mathematical reasons. The proof, it's in there. It wasn't intended to be in there, but it's in there. Again, because of this correspondence of grammatical formalism and the things we use to describe teleportation and all of that. So it is in, the proof is literally in there. The derivation of the tensor product in this situation. Okay. Right, I mean, another thing about these circuits is that they relate much more to the way we think visually about the world and cognition. Let me just now go to the hard results. Okay, quantum algorithms for compositional text processing. I know there's people here who want to hear about algorithms. This is a very recent paper. So the problem of question answering. You got a text, you run a text. This is a Poirot novel. You're running a Poirot novel. You ask who's the murderer. That question is BQP hard for this formalism. So in worst case, it could give you something like an exponential speed up to run a text and ask a question. So there are some assumptions, like you want to have some entangling word, otherwise everything is disconnected. But I mean, a text without entangling words is quite boring, because it means that's like COVID isolation. You know, nobody talks to nobody, nobody interacts with nobody. So, and then you want, and the sort of density of these vectors is always very dense. That's just the result of the word embedding. So these assumptions are pretty trivial. So you could expect like exponential advantage. So this is the theory. We've implemented this recently on our own the H11. This H still comes from Honeywell on the quantum computer, and we did some training, and then yeah, okay. So we did this experiment. It worked. It trained very well. Nice. Like, I'll give you some features about the experiment. Then I stop. So this is pretty much what we did. So you see this dotted line, and on top you see a text. You got like a person going west, and then another person going left, and then one person follows the other person. So it's a story about people following each other and maybe turning around and stuff like that. You'll understand later why I took this example. And then we ask a question: are they walking the same direction or are they not? So this is we did much bigger things than here. I'm just showing this as one. So you have a text about people following each other and walking around in different directions, and then you ask a question: is that person following that person? So it's the example of like I mean, we're still working with fairly small quantum computers at this point, so we can't. But at the moment, we're actually working with BBC data, by the way. So let's see where that goes. And we have two amazing. So anyway, it worked all very well. The results were all very nice. It trained very well. One of the magical things, and this goes back to in the beginning of what I was saying, the trainability problem for quantum machine learning is we can train classical and test quantumly. Because of the compositional structure, you don't need that much context. It's enough to train within a small window, so you can train classically and then test quantumly, so you don't have any training issues. And that's what this graph is showing. Like, see, training is the classical, and then the validation, we check, and it all kind of stays the same. I mean, I'm not going to explain what these little peaks are. They are some sort of singularities, but they're not essential for the result. And then the reason we actually did this following is people were talking to me about ChatGPT, but I'm not like a computer person, you know. I was a professor for computer science 20 years, but I'm not a computer person. And then said, Bob, you should play Chat. I said, okay, I'm gonna mess it up. I'm just gonna try one thing, I mess it up, and I literally did stuff like that. Bob walks out, I was like that, and then I asked like, who's following who, and it completely messed up. It was really bad at this stuff. So that's why we went for this example, so it makes a nice case, like, we're even outperforming these humongous large language models already on a quantum computer. Yeah? And so yeah, so this was the question we asked, and this is the answer of ChatGPT. And it's sometimes really funny, like sometimes it gave the right answer, but then in the middle there was a sentence just randomly: Alice follows Bob, and therefore Alice goes in the opposite direction as Bob. Just like a sentence. Okay, in the reasoning. Okay, now out of time now, so I stop. So soon we will get you can find a version of Lambek where we have all this text stuff going in. We're implementing it. We're probably releasing it somewhere in December. Like, so you can play with this stuff around yourself. Okay, thank you.
Thank you very much to Bob. Do we have any questions or comments?
So in your encoding of natural languages and sentences, in a lot of languages there are a lot of nuances that are not just in the words, but it's like about the order of words in the sentence, like in Latin, how you highlight certain things. And
yeah.
It's so different across all languages, and I was just wondering if you're talking to language experts about how these additional nuances can be incorporated.
So there's two things, like word order can be a nuance, it also can be pure bureaucracy. For example, the way I think about it is these circuits are really more fundamental about meaning. Then we as humans, we have to put everything on a line, so we have to make choices, and the choices are the word ordering. And the French did a different choice than the English, of course, for example. And so that's pure bureaucracy. You have to make some conventions. Now, once you are within this realm of conventions, you can start doing poetry and saying, okay, let's, because you got some freedom there, let's figure things out in a very nice way. And linguists have, of course, done a lot of work on this, trying to capture that stuff. This is kind of below, that nuance is below where we're working here, but this can be done, of course. Like, people have put a lot of work in there. There's also the thing that language evolves, and what was grammatical, what was not grammatical 10 years ago is grammatical now. I mean, if you listen to the kids speaking and stuff like that, again, we notice that with these circuits can deal much better with it because they've got less structure, like the word order, bureaucracy and stuff like that is gone. So it's more flexible to mistakes. But then it's of course also less the sort of kids speak you lose in the process. So, but you could add it. It's just adding extra structure if you want it. But I think there's something nice about going minimal here, just for practical reasons.
We have one more quick question here. Sue?
Do you have can it handle loops, and also with that can it handle conditional statements which do arise in natural language, but loops which also would arise in programs, computer programs, and even like if Alice interacted with Dorothy, who was a quantum object, you had entanglement.
It's a very good question. If you look, of course, if you look like a movie like Memento or something like that, things go backward. So meaning does flow backward, and it's something we were looking into, because if you implement stuff on a quantum computer, you're going to do things unitary. And unitarity comes with like an imposed flow of time. So you want to add loops, maybe to account. And then the question is, do you have to? So that's something we're testing, actually. So it's a very good question.
You think you'll use it for computer programs then, if you can make that work?
But meaning flows backwards when you speak. Like something that you say later actually can basically impact like something that you said in the past and affect the meaning or change the meaning. So yeah, these flows go up and down, and it's something you have to deal with. So it's totally present here.
Okay, so I suggest we postpone the rest of the questions to lunch or whatever. So let us thank